All right, we're going to finish up our talking about work and energy today and come up with a definition of mechanical energy. So let's begin by looking at a simple example. So suppose I take my book here at the initial position and move it up to some final position, a distance y above where I started from. So I lift my book from initial to final position y. How much work does gravity do as the book is moved upwards? So think about this and tell me what you think. Okay, so if we look at a picture, mg is straight downwards. So in this case, the force of mg is opposite the displacement. And so we know what that means is that work will be negative. And so it'll be the force times the distance. And you can think about it as being times a cosine of 180 if you want, get a negative 1 there. But either way, work is hindering this displacement. So we get a negative mgy. And this will be a general situation here. So like I said, you can think about it as being cosine 180. mg is the force. The displacement is that distance, y, the height. And so we get a negative mgy. Let's look at another example. A crane lowers a girder into place at constant speed. Consider the work Wg done by gravity and the work Wt done by the tension. Which is true below? Think about this and we'll talk about it in a second. Alright, so in a situation like this one here, so you can think about there being some cable holding up this girder or whatever it is, and so the forces, there's a tension force upwards, and then there's our good old gravity mg downwards. And the velocity, the displacement, is in the downwards direction. So mg would be doing positive work, and the tension would be doing negative work. So let's think about conservative forces, and so we're making a definition here. For a conservative force, the work done does not depend on the path taken, only the starting and finishing points matter. Example would be gravity. For a conservative force, the work on a closed path is 0, meaning that if you start at one point and move around and come back to that same point, the total work done would have to be 0. So this is true for gravity. If I move the book upwards, okay, there's a negative work done by gravity. If I move the work downwards, it's positive work. It totally cancels out. Where friction, if I slide it on a floor, it always is against the motion, and so no matter where I end up, it's always a negative total work done. Another example would be like a roller coaster. Okay, at the top of the roller coaster, you have the same kinetic energy or same potential energy as you do if you get back to that point again if we neglect friction. So this semester we'll have two forces that work that way. So these conservative forces are very special: gravity and springs. We've talked about both of these already, so we're defining these as conservative forces. A non-conservative force would be anything else in this semester. Okay, later on when we get to next semester we'll talk about electricity and magnetism. These will be conservative forces too, but for now there's only two kinds of conservative forces. Anything else is non-conservative. And we're going to find that conservative forces always can give objects a potential energy. We've already seen this, but we're going to define it a little more practically here. So potential energy, again, is stored energy. It depends on the position or configuration of an object, and our two big examples are the potential energy due to gravity and that of a spring. And our real important equation here is that, again, like we were saying, we get a potential energy from a conservative force. And so if a conservative force does work, all right, the negative of this work is the change in the potential energy. That's how we define potential energy. Now, we kind of just sort of came up with it before when we talked about this, but here is a definite definition. And so let's look at the work done by gravity. So here again, if I'm moving this book from the initial to the final, okay, if I look at the work done, well, the force is mg, and then again, we were talking about here, if I move it upwards, gravity is doing negative work. So inside here I get negative mg times the displacement. Well, with this negative over here, what that does is it says that the change in the potential energy is positive mg delta y. And hopefully that makes sense. All right, so if you lift the book upwards, like in this case here, all right, gravity does negative work. However, the book gains potential energy, right? If you lift it up, it's going to have more gravitational potential energy. If you let go, it'll be going faster when it hits the ground. And so it's real important in this relationship here that you have this negative sign. So it's basically the work done by the conservative force. That's really important. This is the work done by conservative force. The negative of it is the change in the potential energy. And so by moving the block up, or book, or whatever it is, it gains potential energy of mgy. And so this goes back to our definition that we had for Yogi the Bear. So our work done by gravity would be like this here. So again, the work done, if you lift it up, is mg negative y. But again, when you lift it up, you're giving it potential energy. And so that's where we get this definition that we've been using for our potential energy, which is mg times the height. Okay, again, by doing this, we call some place to be 0, which generally we call the height to be 0 here down at the bottom of the cliff or whatever we're talking about. But again, it doesn't matter as long as you're consistent in your own problem. If we look at our work kinetic energy theorem that we described last time, the total work equals the change in kinetic energy. Well, I can split this up by the work done by conservative forces and the work done by the non-conservative forces. So this is the work done by gravity or a spring. This is the work done by anything else. Now we know that, so we can swing this around algebraically, basically bring this guy to the other side. So I got negative W, work done by the conservative force. And our definition is, again, that remember delta U equals the negative of the work done by conservative force. So here's a negative work done by conservative force, and so I can split it up here and write this as delta K plus delta U equals the work by the non-conservative forces. So Knight talks about this equation right here. And from this, we can finally develop our conservation of mechanical energy. So the mechanical energy is defined as before as the kinetic plus the potential, and here we say, okay, work non-conservative equals delta K plus delta U. We can write this out as K final minus K initial plus U final minus U initial. Then we can swing that around a little bit and group up like terms that are both finals or initials. So I'll have a KF plus a UF minus a KI plus a UI. All right, and so we get that the work non-conservative equals the mechanical energy final minus the mechanical energy initial. So be careful, here I dropped a little subset where you write mechanical, and this is something that we do sometimes, basically because we write this so many times. We'll oftentimes just write E instead of E sub mechanical, but here I'm saying that this is the final mechanical energy minus the initial kinetic energy, and that'll equal the work done by the non-conservative forces. So what this really means to us is if the work done by non-conservative forces is 0, then we get that these mechanical energy initial equals mechanical energy final, and so right now we can then say this is the conservation of mechanical energy. And the definition here, so if only conservative forces are doing work, so if there is no work done by the non-conservative force, we can conserve the total mechanical energy. And this basically means that the K plus the U is a constant. It doesn't change. And we've dealt with this problem already. Hopefully we're pretty familiar, but here's the actual foundation that it's built on. So both K and U can change for our particle, but the total remains constant. Now, we haven't quite talked about work by a non-constant force. And so the definition of that would be an integral f ds. Okay, and basically what this means is this integral is just the area under the f versus x curve, or f versus s curve, whatever it might be for distance. Okay, so if we do this for our spring force, the force looks like F equals negative kx. So if you look at that, the spring force, it's changing. Okay, if I make a larger distance x, the force gets larger. And so we have to find the area in the curve. And so let's just say I take it out to some distance x1. And so I want to find this area in here. All right, so it's going to be a triangle. This area here is going to be a triangle of x1 would be this distance here. Okay, that's the x. And this distance here would be the force, and it'll be negative kx1. And so we get that the work is 1/2. The 1/2 is because it's a triangle times the height, negative kx1, and then the base x1. And x1 is just the distance that we stretch the string out to. And so if I do that, I get 1/2 kx1 squared. And then remember, our definition says that the change in the potential is equal to the work done by the conservative force, so these negative signs cancel out, and we get our definition here for the potential energy due to a spring force, which is 1/2 kx squared. And then this allows us then to basically write this monumental conservation of mechanical energy. And so the rule says that when only conservative forces are doing work. But of course, in our class, conservative forces are gravity or a spring. And so we can basically break that down as this is good when only gravity or a spring-like force are doing work on an object. We want to talk about power because it's something we're going to be using a lot. The average power is the rate at which work is done. Okay, so it's obtained by dividing the work by the time required to perform the work. And so average power will be energy or work, okay? So how much work you're doing divided by time. And this is a new unit, joules per second. You're probably familiar with this from light bulbs and such. This is the watt. This is the unit of power. So it's how much energy you're doing, how much work you're doing per time. And so here's a give it a try problem. 4 students run up the stairs in the time shown. Which student has the largest power output? And so what we're saying here is they're walking upstairs, and then we tell you the time it takes to do that. So think about this and give us a go. Okay, so this one here is answer would be B. And the idea here is the power is equal to, you can think about it as being the work or the energy divided by the time. And so here, the work the students are doing would be mgy. And the time is just the time given. And so what you got to do is look at all 4 of these students here and find mgy. And so for instance, you have to take their mass, 80 kilograms times g times their height. Okay, and so you look at the first 3 people are all going a height of 10. Okay, but the 2 A and B are a little bit heavier than the 64. And so they will actually do more work. A and B does more work than C. Okay, but because B does it in a shorter amount of time divided by T, B would be less work. Now C does it in the same amount of time as B does, but she does less work. And then finally this D is a little bit tricky. It does much more work, but in a much longer amount of time. So if you do this equation for all 4 of them, you come out with B as being the winner here. Okay, thank you.